What's up? This is Physics 2212 Lab 2 titled Tape Revisited by Jackson Green Quorum. For a brief little introduction, the purpose of this lab is to observe and create a computational model of two charged tapes as line charges exerting an electric force on each other to estimate the amounts of charge on each tape and compare it to Lab 1. The results are that from Lab 1 we found that the charge was 2.9 times 10 to the negative 8 coulombs, and in this lab we found a more precise answer, 2.9876 times 10 to the negative 8 coulombs. Our fundamental concepts are simple. It's Newton's second law, which states that the net force on an object is relative to the acceleration on the mass of the object, given by the equation F equals ma. And our next one, Coulomb's law, which calculates the electric force between two charged particles and tells us whether the force is attractive or repulsive. We can see that through the electric force is equal to 1 over 4 pi epsilon naught times q1, which is the charge of the first particle, times q2, which is the charge of the second particle, divided by r squared, which is the total distance, or a unit vector, or a magnitude vector, times the unit vector. And sometimes k is written as 1 over 4 pi epsilon naught, which equals 8.99 times 10 to the ninth. For the experiment overview, it's simple. Our initial conditions states that our tape mass is equal to 0.0002 kilograms and that our tape length is 0.2 meters, which we measured out as 8 inches. Our system is the tape on top and our surrounding is the tape on bottom, and the distance when the electric force affected the tape on top was 0.034 meters. For our computational model, let's review. From Lab 1, I had this, and which gave me this output. But for line 2, things changed drastically. I'm defining an electric field. We can see here everything listed out. I'm given my universal constants up top, the mass, the charge, and the tape length. Defining the electric field, and then this iteration over here creates the lines themselves. So the code on your left, first I'm scaling the electric field vectors so we can see them on the visual, and then we're iterating through each piece of tape, integrating. This code is the integral. So then on the right, we are applying the net electric and gravitational force, allowing our arrows to come to life, and then we are printing out our results. Our computational model uses these two equations right here, and the outcome over here, as you'll see, the magnitude of the electric force, 1.91408 times 10 to the negative third, and the magnitude of the gravitational force, 1.91295, we are right in the ballpark of being equal, which is exactly what we wanted. Our green arrows show that the electric force of the tape on top goes up and out, and our vectors are included, which is amazing. So for a compare and contrast, our point charge model, 2.9 times 10 to the negative 8 versus the 2.9876 times 10 to the negative 8. We saw this before. It's amazing. Some of the assumptions we had to do to get here was that we neglected air resistance. We had to assume that there is the same amount of mass for each tape, and that our Lab 1 models are in fact point charges, and that the Lab 2 models are evenly distributed throughout the tape. The charges are evenly distributed throughout the tape. Sometimes that doesn't happen because, certain things in the atmosphere might be inducing a dipole moment, so charges might not be evenly distributed. But in order to do this, that was one of the assumptions we had to make. So a possible source of error, mass of the tapes were calculated, not measured directly. We didn't put them on a scale and have something tell us what it was directly. We calculated. And precision sometimes messes with the outcome. Other forces we're not considering since we neglected air resistance and air pressure. If one were to be in an environment where air pressure is significant, that would definitely halt the tape's movement by the electric field. And charges were not equal due to grounding by human hands. This is true. The tape on top could have had the correct charge, but since we had to handle our tape, it could have grounded it. Time for our discussion. So what if I had modeled each of my tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model. We would have gotten an outcome that looked significantly different. We would have only gotten a few electric field vectors going in each direction rather than a bunch of electric field vectors pointing upwards and outwards, which is how we got the model in the first place. Why do these estimates differ? Which value is more likely to be closer to the real value and why? Well, they differ because there were different types of calculation. The first one's pure algebra and vector analysis. The second one is a form of integration, which precisely adds up each differential section of charge. Precisely. The line charge is more realistic since it takes into consideration the length of the tape rather than concentrating it to a single point. But anyways, this has been Lab 2 by Jackson Green Corm. Hope y'all enjoyed. Thank you for your time.